Hi, my name is Marcus Pereira, and I will be presenting our work on safe optimal control using stochastic barrier functions and deep forward-backward SDEs. In this work, we propose a novel algorithm for safe reinforcement learning and architecture to solve constrained HAP equations that ensures safety not only of the learned policy but also while learning the policy, is end-to-end differentiable, and combines the principles of safety and optimality into one framework. We achieve this by bringing together stochastic control barrier functions, deep forward-backward SDEs, and the OpNet differentiable convex optimization layer to produce an end-to-end differentiable, safe stochastic optimal controller. Now let us take a look at each of these building blocks. We start with stochastic CBFs, which extend deterministic CBFs to stochastic systems. More formally, suppose that we are given the dynamics of a system where x, u, and w are time-dependent state, control, and Brownian noise vectors respectively, a hand-designed and task-specific barrier function, and a safe set that is a zero superlevel set of the barrier function whose boundary is where the barrier function goes to zero, and suppose that we also start inside the safe set. Now, assuming that there exists a control that satisfies the following safety constraint, the probability of staying inside the safe set for all time is 1. Notice also that the left-hand side of the constraint is the Ito derivative in contrast to the regular time derivative in the deterministic case. Next, we look at deep FPSDs, which are deep learning architectures that solve parabolic PDEs. This is achieved by the nonlinear Feynman-Keck theorem that links the unique solution of parabolic PDEs to systems of FPSDs. The HAB PDE arising in stochastic optimal control problems is in fact a parabolic PDE. Deep FPSDs utilize the nonlinear Feynman-Keck theorem to solve for the value function and its gradient to obtain the optimal control. Finally, we look at the OpNet differentiable convex optimization layer, which generalizes a neural network layer as the solution to a quadratic program. In the forward pass, an interior point solver outputs the solution to the QP. Notice that the inputs to this layer comes from activations from previous layers, which could be regular neural network layers or other OpNet layers. In the backward pass, instead of using autodiff and backpropagating through the unrolled interior point solver, the KKT conditions are used instead to compute gradients efficiently. This allows computing gradients with respect to any of the layer parameters, which could be components of the objective function or of the constraints. Putting all of these components together, we have the dynamics forward SDE and the value function backward SDE coming from deep FPSDs, a QP to compute the optimal control at each time step handled by the OpNet layer, and finally, the safety stochastic CBF constraint inside the OpNet layer. We now look at our proposed deep network architecture. We are given an initial state and a terminal loss function that allows us to compute the terminal value and its gradient. Since we want to avoid backpropagating the backward SDE, we make the unknown initial value function a trainable network parameter and the known terminal value and its gradient as prediction targets. Next, we initialize the weights of the network. The network is used to predict the gradient of the value function. This in turn is used to forward propagate the value function with sample noise. The gradient is also fed back into the OpNet layer to compute a safe control, which is then used to forward propagate the system dynamics with sample noise. The new state is now fed back into the LSTM to predict the value function gradient at the next time step. We now repeat the process of forward propagating the value, computing a safe control, and forward propagating the system dynamics. This process is now repeated until the end of the time horizon. Finally, using the known terminal cost function, we compute targets for the predicted value and its gradient and compute a loss function, and train the network using any SGD-like optimizer. Presenting some highlights from our simulations, we start with the cart pole balancing task with a time horizon of 1.5 seconds. In the following video, the gray boxes are cart position bounds while the red area represents unsafe pole angles. As seen in the video, the unsafe controller blind to both constraints completely violates them in the initial iterations. Next, we impose pole angle constraints, which allows the controller to save the pole from falling by moving very fast in one direction, thus violating cart position bounds. Finally, with both constraints imposed, the controller is able to stay safe for the entire time horizon. In the end, they all learn the same control policy, thus highlighting the need to stay safe during learning. Our next example consists of 4 2D cars starting at 4 corners of a square grid with the goal of swapping positions with a diagonally opposite car while avoiding collisions. Initially, the cars move towards the center and stop short of their targets to avoid collisions. However, these states get associated with a high cost or high value and are thus non-optimal. Therefore, as seen, the cars try going around the targets to avoid the non-optimal states. As iterations progress, the controller tries to strike a balance between safety and optimality. Finally, they figure out a strategy to move towards the center, orbit around the center, and move towards their respective targets. Thanks for your interest in watching this video.